All right, welcome back. This is the last configurations with regards to this problem here. All right, now instead of having ABC in the previous configuration, we can also have the system S in these configurations where the A is shown here, and then B is here, C is here, and then the mass 3M is attached to C, and then whereby the mass 2M is attached to B according to the diagram here. The BC still has a length of 4A, AB is still 3A, and then whereby AC is 5A, but the configurations is a little bit different in this case. Now the same thing, we have to set up our reference frame in this case. Okay. Now again, you can see that the origin in this case is set at B here. All right, and then the same thing, we are going to make assumptions where the center of mass will be located. So it will be located roughly something like this, where the x bar is a vertical distance measured from the line AB, whereby the y bar is a vertical distance measured from um, line BC in this case, right? So from here, we will be able to obtain the center of mass x bar and y bar itself, right? Now you can see that x bar and y bar itself. Okay, right. So we're going to apply the same principle of moment to work out the center of mass x bar and y bar in this case with respect to our reference frame in this case. Right. Now the same procedure here, we will have 17M, then based on our center of mass configuration, we have this, and then is equal to the sum of all its individual moments for all the components in this, or that components that made up these rigid bodies here. So I'm going to start off from um, anyway. For instance, in this case, I'm going to start off from the length BC that has a mass of 4m. That will be 4m. It's located at 2a 0. And then next I'm going to move on to here. It has a mass of 3m. So there's 3m. That is located at 0, 1.5a. And then next I'm going to work this out. It has a mass of 5m. So there's 5m, which is located at about 2a and 1.5a here. And then lastly, I'm going to include the mass 2m and 3m in the calculations of the moment. That will be 2m. Again, 2m is located at the origin there, so it does not produce any turning effect. Then we have 3m. 3m is located at 4a 0. All right, and then there you have it. We can simplify these calculations as such. So we have 8a 0. So there's a 0, 4.5a. And then here you have 10a, 7.5a. Then we have a 0, 0. And then finally we have 12a and a 0 here. And then if we try to simplify this, we have 30a, and then this is 12a here. Therefore, I can conclude that based on this configuration, I can write this as 30 over 17a, and then 12 over 17a here. Now bear in mind, this measurement is with respect to this frame of reference, which is x bar and y bar here. All right. Now I hope that's clear. Again, the distance the distance of the center of mass from A itself. I'm going to write that down one more time. This is also XA bar. All right. Now, if you try to determine how far is this center of mass with respect to this position here, now XA can be calculated as 3A subtract off with a Y bar instead. Okay, in this case it's Y bar. So we have 3A minus our Y bar is 12 over 17A, which yield 39 over 17A there. And then the vertical distance with respect to this line AB is the same as X bar. So therefore, it still yields the same result as our first and second configuration. Now that would be our checking strategy in the exam. All right, I hope that's clear. And then lastly, I'm going to show you how we're going to work out the angle between line AB with respect to the downward vertical lines. All right, now stay tuned. Okay, our second section, this is how it looked like. Okay, now I'm going to show you a short animation just to show to you how this structure is being hang from A, and then where the line that passes through the center of gravity or center of mass actually look like. All right, now this is how it look like. The rotation wise, you can do it counterclockwise or clockwise. Doesn't matter in this case. What is important is when it's hanging in equilibrium, the lines of gravity that passes through the center of mass would be shown here. Right now, this is our center of mass. Now we are still interested to obtain this angle here. So the easiest way is to figure out this length here, which we have already worked out just now. This is the same as what do we have here? This is the same as 30 over 17a, and then the distance of the center of mass from A is we have already worked this out, whereby the X bar, okay, or you can use a Y bar, doesn't matter in this case, is actually 39 over 17a. And then therefore, by using the, or by configuring, by considering, sorry, by considering this triangle, so I'm gonna consider this triangle PAC again. Okay, we can apply a simple trigonometry tangent, which is given by 30 over 17a over 39 over 17a here, which can be reduced to 10 over 13. Okay, I'm going to rewrite that one more time. And then therefore, we can conclude that the angle between the line AB and the downward vertical is given by the inverse tangent 10 over 13, which yield 37.6. Exactly the same as the angle that we obtained from the tree configuration. So in the exam, no matter how you are going to draw your structure, eventually we will end up with the same center of mass and then the same measurement for the angle there. Now I hope this has been useful to your learning. If you like what you are looking at, don't forget to press the subscription button, and then press the notification bell so that you can receive the latest video. All right, thank you very much for watching. I'll see you again.